starting. In your notes, the last thing you had was Bohr model, correct?
Yes.
How do we feel about making Bohr models?
Pretty good.
Okay, we're going to get a little more practice, but I won't be focusing on that. So if you have a question, feel free to ask. But we're moving on to using the Bohr model and Lewis dot structure to look at how bonds start to form. We're not going to go into crazy depth, thank you, but we will start to look at how those form and why, okay? Questions are welcome, as always. So let's just go ahead and get started with a couple additions for your notes. Valence electrons. Did we mention what they are?
A little.
So if you don't have it in your notes, you need to put it in there. I'm pretty sure I told all my classes. I had it on the board over here too. A valence electron is an electron on the outermost energy level, the outermost shell. Okay? So valence electrons are on the outside. So for example, if we had carbon, it would have 2 rings around it, right? And it would have 2 on the first, and it would have how many on the second? 3? Are we guessing? 4? Are we guessing? No, we know, right? How do we know? Check it out. Put this rule if you don't have it. You're going to find carbon. You're going to find carbon if you weren't here or whatever. Here's carbon on the periodic table. And then you're going to count from left to right until you get to it, but you're going to pause in the valley. So you're going to go 1, 2, pause, 3, 4. It has 4 valence electrons. What in the heck am I talking about valleys? Does this kind of look like this part is sticking up out of there like a hill?
Yeah.
This kind of looks like a hill over here. This low spot would be a valley, right? So as you're counting to figure out how many valence electrons elements have, these all have 1. These have 2. Most of them through here have 2. There are exceptions, okay? And then you'd start counting again here at 3, 4, 5, 6, 7, 8. The noble gases all have a full valence shell. They max out at 8, other than helium, because it only has 2 electrons. So you can't have 8 in its outermost shell. It doesn't have that many. So the noble gases, their electron configuration on the valence shell is full. You can't take any more, and they really don't want to give up any. I guess you could look at it like if we wanted to humanize it, they're satisfied. That makes sense? That makes sense. They're very content. That's why they don't react much at all. You'd struggle to make them react. They don't want to react with anything else. So chemically, we refer to them as being inert. Okay? All of the others want to have valence shells like them. So if we want to humanize it, we'd say everybody else from here on over is jealous of how these gases look on the outside. Is that kind of shallow? Okay, fine. So, but that's the way it is. So they all want to be looking like them. Okay, so what does that mean for us in practical application? Where is erasers are right where they should be. Do we remember table salt? Yes. What is table salt? Wow, it's like just reciting it. Sodium chloride, NaCl. Go ahead in your notes. I'll start you here. NaCl. Go ahead and draw in a Bohr model for each right now. Try to stay ahead of me. I'm going to go ahead and do it too. They're both in the 3rd row of the periodic table, right? Right across here, 3rd row. There's your sodium. There's your chloride. Chlorine, rather. So each has 3 rings. The innermost ring represents the 1st row in the periodic table, 2 elements. So we're up to electrons there. You can think about it that way. It works. And you know what? I'm going to draw it like I think most people teach it. Some might call it the right way. We're going to bunch our electrons in 2s. Like that. Does that make sense? Yeah. Just it's more of the convention. The next row on both will have how many? And the next ring. 8, because the next row down, the second row has 8 elements. So 1, 2, 3, 4, 5, 6, 7, 8. Whoops. 2, 4, 6, 8. 2, 6, 8. And how many valence electrons does sodium have? Just 1. I'm going to put mine off to the side right here because the TV is kind of impeding the visuals. How many does chlorine have? 7. It's 1 shy of having a full set. Now again, if we're going to like humanize these, how does that make chlorine feel? Not good, maybe just a little inadequate. It's so close though. If somebody's really close to like in their mind being perfect, do they get desperate? Okay? So chlorine starts to get desperate. It's like, it's just waiting to make a deal. It's got a blank spot here where it can accommodate 1 more electron. And if it has that 1 more electron, it will have the same electron configuration as argon. It will look the same as argon on the valence shell. It will make it quite happy. And it'll make it more stable. Okay? Sodium has just 1 valence electron. And its dilemma is, well, would it be easier to gain 7 to have the electron configuration of argon? Or would it be okay to lose 1 and have the electron configuration of neon? If we're going to humanize the elements, would sodium care? What would be the difference on the outside, the valence shell, between looking like argon and looking like neon? None. There's no difference. From the outside, they look the same. So let's make it happen. Let's say sodium gave up an electron, and chlorine graciously accepted. Doesn't that mean that now we've got that guy there? Can't I go like this? Yeah, that's what we just did, right? There's no, if without that electron, if there's no electrons in the valence shell anymore, that's not a valence shell anymore, is it? Now this one is. Is it full? It looks like neon, right? But wait, 8 in the outermost for an argon looking, or 8 in the outermost for a neon looking. What's the difference? Who cares? They look just as cool. Okay? Now, what does this mean? They're both ions now because they both either lost or gained an electron. How many protons does sodium have? What is this atomic number, in other words? 11. How many electrons did it have? 11. What about chlorine? 17 protons and 17 electrons. But we just made an exchange. So now how many electrons do we have over here? Okay, let's do some math. What's that leave it with? Positive 1, right? And this became 18. So now we have negative 1. What do opposites sometimes do? So we have an ionic bond. Write it in your notes. Right now, I have it way over here. An ionic bond. I'm going to change this one word out. It still works, but it's better this way. An ionic bond forms when one atom gives... I started to write atom. I stopped at the T. An ionic bond forms when one atom gives an electron to another atom. In this case, we're dealing with different elements. So either way works. And we would call that a give-take relationship, right? Because they have become oppositely charged ions, they're going to stick together. They're going to be electrically attracted to each other. An ionic bond forms when one atom gives an electron to another atom. And again, if we're humanizing them, they're both happy with the arrangement. Why? Because they both feel like, hey, look, I look like a noble gas. Pretty sweet, right? Wait, what do you kids call passion now? Like, is it drip? Is that still a thing? So sodium and chlorine are both like, check out our new drip. We look good, don't we? We look like noble gases. They're laughing. They're laughing at me. That's fine. All right. What would it look like with Lewis dot structures? Well, can I erase this? Just the models part. Can I erase that? It's my whiteboard. Yeah, but like if you were still copying down or if you had a question to ask. The red doesn't erase well. Something about the pigment, I guess. All right, so now I'm going to teach you how to do Lewis dot structures. Did we start at all with that? No? Told you about it? All right, Lewis dot structures right here. I'm not going to use the red as little as possible because it sticks. A Lewis dot structure is a model of electrons, but unlike the Bohr model that showed all of the electrons in their energy levels, a Lewis dot structure only represents valence electrons. Why do you think we might focus just on the valence electrons? They're the ones that determine how reactive an element is. Whether it's going to give, take, or in the next example, share electrons with other elements. How likely or unlikely are they to interact, to play with the other elements? So let's do one. First of all, this diagram kind of shows you how to set it up. So the question mark in the middle, that question mark is a symbol. Okay, so whatever element you're dealing with and modeling, you would put the symbol in place of that question mark. Understood? Okay. Now, the number of valence electrons only, okay, you'll put, if it has just one, you put it where the number 1 is. The dot. You'll put a dot where the number 1 is. If it has 2, you'd put 1 here, you'd put 1 at where the number 2 is. And you continue to fill it in where those numbers are. Does that make sense? Let's try a couple, okay? We'll start simple. Hydrogen, where does the dot go? To the right and slightly up. Right there. Because it only has 1 valence electron, right? How about carbon? How many valence electrons does carbon have? 4. You count from left to right, skip the valley. Good. So we have 1. See where the number 2 is? Put that one there. Go ahead and place the last 2. Follow the diagram. Right here. Is this readable? Do I need to rewrite that? Try to. Is it fine? Everybody have that? So you got 1 on each side. That's very nice. That's very nice indeed. How about, we mentioned argon. What would argons look like? 8, okay, it's because it's got a full set. It's a noble gas. So how many would you have on each side? 2 on each side. Guys, listen very carefully. Do not do what I'm about to show you the wrong way, all right? I have seen this before. This is wrong. Don't put this in your notes. But I have seen this. I'm just showing you what not to do. And I'm going to ask you why you think they did this. This is wrong. Why? Go. It's not showing only the valence electrons. What is it showing? They're trying to show all of the electrons, right? So they've got 18 on there because argon has 18. But remember, Lewis dot structure, we're not concerned with all of them. We only want the valence electrons. That's all we're concerned with Lewis dot structures. Okay? Questions on that? All right. Now, we did an ionic bond example, right? With sodium chloride. We already have on the board, by accident, I didn't plan to do it that way, hydrogen and carbon. Do you remember one of the examples we had earlier, like last week, we talked about methane?
Yeah.
Okay. You remember methane is CH4? Okay. Carbon, you can think about each of these sides as potentially having a docking port. Okay. I could dock an electron right here, couldn't I? I could dock an electron right here. I could dock one right here. I could dock one right here. Hydrogen, if it had a full valence shell, well, you'd put one here and you'd put one here, right? For convenience sake, could I put one there? I mean, it might not be right, but I could do it. All right, so check this out. CH4 methane. Hydrogen pulls up alongside and says, hey, I've got one. I see you've got 5. Do you want to share mine and I'll share one of yours? And carbon says, sure. And it docks. And then another hydrogen pulls up alongside. We're working backwards now, right? And it docks. And another hydrogen. And a last hydrogen. They all dock. All of the hydrogens feel like what now? They feel like which noble gas? They feel like, wow, man, I've got 2. I'm just as good as helium at this point. In reality, it just means they're stable as helium. Okay? Now, what about for carbon's part? How many does it feel like it has now? This is called a covalent bond. Covalent bonding happens when 2 or more, and by the way, that can be 2 or more as well. Ionic bonding can be 2 or more elements combining together to form those bonds. So covalent bonding, when 2 or more atoms share electrons to get to that noble gas configuration. So key terms for ionic bond, it's a give-take relationship. With covalent bonding, it's a sharing of the electrons. You guys want another example of let's do an example of, by the way, first, before I move on, any questions on this example of a covalent bond? You can see that they're sharing. And using Lewis dot structures kind of makes it easy to understand, I think. Okay. Yeah, let's do another ionic bond. Can I erase this? Stop. Not yet? Okay. I'll wait. And for the next example of an ionic bond, I'm going to do one that's not 2, but more than 2, and you'll see how that works. You good? Good? Everybody caught up? Awesome. All right, so we're back to ionic bonding. And this time, did we talk about road salt the other day? Yeah. And calcium chloride. Okay, so we're going to do calcium. And I really do like using Bohr models more for some reason with ionic bonding. And I like using, because of the Lego thing, it works better with, in my mind, with covalent bonding, and Bohr models tend to work better for ionic. Yeah, thank you. My mind is a little slow sometimes. All right, so we have calcium, and we have, hold on, I'm going to put, when you put it in your notes, put it in the middle of the page. Calcium, put it in the middle of the page, it'll make sense, I promise. So we have calcium, I'm going to move that down a little bit. And we have chlorine. Go ahead and do Bohr models for them. Give you head start. Yeah, you got a periodic table back there, and you have a periodic table up here on the TV, whichever is easier for you to use. They're coming. The Kentucky Army National Guard says that they are coming. They're printing them. Periodic tables. Yeah, they're. Where did I have an example? I have one somewhere. It's a mess. I need to clean my desk off. Just slightly. It's a little bit messy. Here's one. It's going to look like that. Unless they came out with a new design. All right, so calcium, how many rings around it? 4. Check again. Look at the periodic table. Calcium, we got 1, 2, 3, 4 rows down. So we're going to have 4 rings around it. And chlorine is going to have the 3. And we're going to go ahead and place our dots, do them in 2s again. So we're going to have 2 here, 2 here, 2, 4, 6, 8, 2, 4, whoops, 6, 8, I need my 4th, don't I? 2, 4, 6, 8. And then how many on the valence shell for calcium? 2. So I'm gonna put one here, and I'm gonna put one here. I guess I'll do it the right way. That works too. And then how many for chlorine on the outside? 7 valence electrons. So we're going to go 1, 2, 4, 5, 6, 7. And I'm intentionally leaving the blank spot right here. So it's a familiar setup, isn't it? We know chlorine wants one more to have a full set. It would then look like argon. But what about calcium? It has 2 to give up. So we can assume, well, yeah, I'd want to give up 1 to chlorine. If that exchange happened, would calcium be positively charged? If it got rid of an electron, yeah, it would be positively charged. But would it be happy? No. It still wouldn't look like a noble gas. Would this chlorine be happy? Yeah. Sure, if that were to happen. But in nature, what we end up seeing, the conditions are right. See what I'm doing? Put another one on this side. Put another one on this side. Another Bohr model of chlorine. 2, 2, 4, whoops, 6, 8, and then we have our 7. And this time, I'm going to put the one that's missing over here. What's about to happen? Guys, so check it out. The last one we did for ionic was sodium chloride, NaCl. What is this? CaCl. How would we write it? Yes. Ca, calcium, Cl2. Because it's got 2 chlorines. Does that make sense? Calcium needed to dump 2 electrons so that it would, so look, like we did before, if calcium can get rid of these 2, what does it look like now on its valence shell? It looks like a noble gas. So it's satisfied now. It's gotten rid of those 2. but it needed 2 willing partners now to take those. Chlorine can only take 1, so it took 2 of them to take the 2. Does that make sense? Ask the questions if you have them. By getting rid of those 2, that valence shell is gone. It drops back to the next inner one, which is full. Yes? These electrons?
Yeah.
They're just models of the electrons.
I understand how to get the number.
The number for them for each level or just all together? All together, it's going to match the number of protons. So for calcium, the atomic number is what? 20. So it would start, like we did before, it would start, check this out, this is good. It would start with 20 and how many electrons? 20. It'd have 20 protons, red for protons, positive, right? And it'd have 20 electrons. But now it's getting rid of 2, so it'd have what?
18.
So we have 18. So we have what kind of a charge? Positive, because you got rid of negativity. Electrons are negative. Okay? And then over here, remember these had 17 each protons, and they had 17 each electrons, but now they have what? Now they have 18, which means they're going to be negative. It's still opposite, right, as far as the charge? You still have positive attracted to negative. Does that answer your question, though? Kind of, sort of?
Thank you.
So we get the total number of electrons to put on our Bohr model to start with from the periodic table. If it's not an ion, it will have the same number, 20 and 20.
So 8, there can only be 2 on the first ring, and then 8.
Correct. There can only be 2 on the innermost ring because there's only 2 elements on the first row. It makes sense. It makes sense, and then it doesn't once we get into the 4th row. But then we'll make it make sense again. Yes?
So say you use titanium and it needs to get rid of 4, you could do like 4,
Could I do like...
like if it was 4.
Oh! Okay, so I'll do a generic example for you. I'll talk in generalities because specifics would make me probably do some research, okay? If you're, let's say you're here, like carbon, and you have 4 docking ports, that makes you very likely to make covalent bonds. But it makes you very unlikely to make ionic bonds. Why? Because you'd either have to gain or lose a lot of electrons, right? For carbon, it'd need to gain 4, or it would have to 1, 2, 3, 4 to get back there. So it's more likely to form what type of bond? Covalent versus ionic. Also, something to think about. What's this dividing line? Metals to nonmetals, right? So the metals are over here. The nonmetals are over here, mostly, right? We've got these metalloids down the middle. If you want to bond a metal with a nonmetal, what type do you think it'll use? Ionic. So if you got to pick between ionic and covalent, if you're doing nonmetals to metals, you're going to be more likely to be forming ionic bonds because the metals only have 1 or 2 valence electrons. They don't have to lose many. And over here, these, especially over here, they're more likely to want to gain 1. Okay. Now, what about if we're nonmetals bonding with other nonmetals? Now you're going to be covalent. Okay. So nonmetal. Put it in your notes. Put it in your notes right now. That's a good one to remember. I don't think we really need that this year, but for chemistry, in a couple of years, you guys take it junior year, right? Chemistry? Is it sophomore? I always get confused. Whenever you take chemistry, by the way, you'll do some chemistry in biology. Okay. Thank you. She's keeping me focused here. What are we writing down? You're writing down nonmetals to nonmetals, when they bond, they form covalent bonds. Nonmetal to nonmetal is going to be covalent. Nonmetal to nonmetal is covalent bonds. Nonmetals to metals form what? Ionic bonds. Could we have metals to metals? We wouldn't call that ionic or covalent though. Instead, they form alloys. We melt them down, and they like, I don't want to use the word share because they'll confuse you, but the electrons are just in this like giant shared sea of electrons. Okay. Yes.
If they're like metals to metals or
Yes. Yes, I like that. I would much rather. It's called a metallic bond. So metal to metal forms a metallic bond. Generally, it's going to be an alloy. But if it's all one type of the element, one type of metal, then it would just be a metallic bond with. You wouldn't call it an alloy. Is a mixture of metals. Okay. An alloy is a mixture of metals. Yes.
Why should every member except for one of the
Ah, good question, guys. Hey, let's do just a few like general knowledge with the periodic table things. He asked, why is 113 not there? It hadn't been discovered yet. Since then, it has. I think they've extended it out to what, like 117 or something.
118.
Is it 118 now? Okay. Yes. Alloy, A-L-L-O-Y. Another question that I had earlier today. It depends on the periodic table, okay? This one, you see these are all black colors, but then there's a couple that are like blue colors. What is that all about? So, I don't know about this one. The one on my back wall, the blue is liquid at room temperature. There's a discrepancy between, like these are blue, and the ones back there are black though, so I'm not sure. But back there, for sure, I'd have to look it up if francium and cesium are liquids at room temperature. But that's what that is. The reds, see the reds? Those are gases at room temperature. Blues are supposed to be, I'm looking for, yeah, mercury's blue there. So I think it's at room temperature, they're liquid. And then the blacks are solid at room temperature. Good. Down here, they don't have it. The one on my back wall, the man-made elements are actually whited out, so they have a black outline, but the letters are white. Do you guys see that on the back wall? That means they're man-made. Okay.
What's the difference between the bottom and why is it cut off from the
Oh! All right, so the lanthanide and actinide series, these two cutouts, if you look close, we've got number 57 here, and then it jumps to 72. 58 through 71 are down here. They would go right there. But if we had them there, this rest of the row would get kicked way out, so like over here. Does that make sense? And then we would no longer have radon, for example, in the noble gas line. We want to preserve the shape because the shape helps us understand properties and characteristics of the elements. Does that make sense? So we just like, hey, we're going to pull that out and put it down here. Same thing with the actinide series. They just, it would go in right here, but it would shove everything else down. Yes?
So would the bottom be row 8 or would it still be?
No, yeah, this would be row 6. This would go up in here. 7, this is row 7. It would go in there. It would just, so rows 6 and 7 would be out to like here.
But why is it row 7 with row 7 because like
This whole row from 90 to 103, 89, 104. See that?
yeah, but there's like blank spaces on the
These are ones that had not been discovered by the time this was made.
But if you look back there, they
how
have
do we go through some stuff?
Yep.
That's what I don't get.
Or they have placeholders.
still make that
How does it just not discovered?
Guys, if they continue to discover more elements, will they have to either extend, guys, would they either have to extend it out further or maybe make another row? I don't know. I'm not a chemist. Yes.
Would the ones on the bottom still follow the balance rule or ions? Or electrons?
Yeah, so most of these would have 2 valence electrons. But remember, because they go in the valley. Okay, but remember, there's exceptions to that. Also, do you recall from the documentary, side conversation? If you've got something you want to contribute, that's great. Okay, but do you remember the lanthanide series? This is where we have the rare earths, and they were saying that from the outside they all look like each other. That's because most of them have, at least most, if not all, I'd have to look it up, have 2 valence electrons. So they're hard to tell them apart. Yes?
Why those? Like, why do they keep those? Like, why not take the other one?
So up here, there's enough room.
Yeah, I know that. But like, why those numbers? Like, is there
Just the way nature worked out. So we take, look, the chemists that came up with the periodic table looked at the natural world, made sense out of it the best they could, and found this shape to be the most useful. Could you make a periodic table with a different shape? Sure. They arrived at this because they found it most useful. I've seen one, you can look it up, you might find it interesting. There's a spiral-shaped periodic table. And I don't even remember why that was useful, but somebody thought it was more useful than this for some things at least. We got a lot of time now. A little bit of time left. Let's see, what else can I teach you guys, or what questions do you have about the periodic table? What else? Huh? You would probably like to read about Mendeleev and how we got to this shape. Like, history of the periodic table. What?
This is another shape.
Yeah, no, that gives me a headache. What was your question?
I forgot.
Oh no, I waited too long. If you remember, please, yeah, that's crazy, right? You won't have anybody teaching you about that probably, unless you look it up on your own until you get to college. And even then, probably unless you're taking upper level chemistry. So unless you were actually going into a chemistry field. Yep.
So what sort of bond is created to break glucose?
Glucose?
Yeah.
So, all right, perfect. This is good. I love it when questions help reaffirm what we were saying. So glucose, she asked what type of bond would be to form glucose. Well, glucose is C6H12O6. Remember, is it a metal or is it a nonmetal? Carbon. Non-metal. Hydrogen. Most of the time. Oxygen. Non-metal. So if we've got all non-metals,
then it would be
covalent. This is a covalently bonded molecule. And sometimes you'll have single covalent bonds. There's also double and triple covalent bonds. Yeah.
So with both carbon and oxygen bond to hydrogen, is that how it works? Because
So carbon would probably be at the center. We could pull it up if you'd like.
Yeah.
Let's pull it up. Yes, question? I can't hear you because everybody else is talking. Shh.
non-metal bonds with a non-metal is possible for it to
Probably very unlikely. You could Google, are there any examples of that? You could probably look that up. All right, so glucose molecule chain. Let's take a look and drag it over so we can all see. Get off of. All right, so here we go. Check it out. You guys are in advanced class, so this is good. All right, so we have down the middle, what do we have? Carbon, because carbon is it's a backbone, right? Backbone of life. All right, so we have carbons down the middle. Each single line is a single covalent bond, okay? If it's a double line, they're sharing more than one. It's a double covalent bond, okay? So yeah, you got all these different things going on there. What's up?
Is that like kind of like DNA?
Yeah, in fact, we can pull that up too if you'd like. Mouse, where are you? Chemical formula. Well, DNA is a long chain. Let's see what it pulls up when we pull it up, though. Yep. So here, and if this is over your head, guys, I'm not going to test you any of this stuff. I'm not at this level, okay? But can you see how there's double lines and single lines in there? That's showing whether it's a single or double covalent bond. And I'm looking to see if there's any triples. I don't see any triples. That's pretty cool. But if you see, you guys see where there's a P surrounded by oxygen? So you could have peroxides, no, not peroxides, phosphates. So phosphorus with oxygen in whatever configuration are phosphates. The ones with nitrogen at the core, those are nitrates. Okay, so kind of neat. Yes?
How is the Ionic bond like?
There are none there.
No, I know there's none there.
Oh, well, they're not going to show them with lines like that. I'll have to look it up. I don't think I've ever shown it any other way. All right, you got about 3 minutes left. Yes. Did you get the question? Shh. Everybody, shh.
Okay, so going back to like the elements on there, it's like, can you make Bohr models out of those?
Bohr models, yes, you could. It would be a task.
Okay, so so say you were like making a Bohr model out of like, I think you guys say like 80
Okay.
I've got the very end, like 70.
70.
Oh, right here.
Yeah.
Okay.
So if you were to make a Bohr model, would you just like add all those like numbers in, like just like dot and the other one?
So, what row would it be in? 6, right? So you'd put LU in the middle for a Bohr model. You'd do 6 concentric rings, and then you would fill in. You can't see very well on the side of this periodic table, and I have it written on the back one there. It shows how many each ring would take, each orbital would take. Okay, so right here for the row you're asking about, it says 2, 8. That's really small for me to read. I can look back there better. It says 2, 8, 18, 32, 18, and 8. That's the maximum amount to be able to take, and it is all the way on the end, almost. I don't know. So it'd get close to that, but I would have to look that one up because it's in the transition elements. It might be one of those goofy special cases, but most of those only have 2 as the outer. The rest would go in the inner. Okay? Yeah. We would have to do them onesies, one at a time, and I'd have to look it up because there's exceptions to the rule. In your tracker, I put the videos. I did it live with you guys, but there are videos that cover the same stuff if you needed that. It's in there in the tracker. That's all I got for you.